Welcome to another R tutorial. For this tutorial, we're going to review some functions to summarize numerical data. And we're going to apply these functions to the analysis of a data set we had examined earlier when we had looked at examination or exploration of the row subsets of a data file. And this is a case of an application of data analysis of statistics in the realm of psychology. In particular, we're looking at youth attitudes toward the relative ranking of particular attributes or the relative importance that they ascribe to various attributes. And this is a survey of children in late elementary school surveyed in the United States, and it is based on an actual psychological survey. Today, I want to emphasize several kinds of measures of statistics and several functions here. We're going to begin with an overview with a function in the Mosaic package that is appropriately titled favstats. Often, statisticians will refer to a 5-statistic summary, which is typically, the average or the mean, then the median, and the min and the maximum, and maybe some kind of interquartile range. And we're going to not necessarily review all the concepts there, but the general emphasis is on two features of numerical data that is important to distinguish from categorical data. With numerical data, we have rankings, we have distributions. And so we have really two measures. We have what is the central tendency, on average, where do you lie? And then we have the spread. Now, of course, you can have different distributions. What are called bimodal distributions would be one where you have two different peaks and valleys. You can have very complex distributions. In general, though, the descriptive statistics that we use to analyze numerical data and the functions we're emphasizing are approaches to understand the central tendency. On average, where do these numbers lie, as well as the spread. And I'm going to begin with the overall summary statistics because that will give us an entree into the mean function, which is the average, the median, which is that value that splits the sample in half, and then various measures of spread. So here we include the standard deviation, which is a measure of how much on average does the sample deviate from the average. Variance, which is related to standard deviation, as we'll see. And then we'll look at range, which is really simply the maximum and the minimum. And then we'll look at the interquartile range, which is a measure of central tendency, you could say, because it's a way of splitting the sample into first a half, and then each of those halves into halves. So you have 3 segments that split basically in the same way you'd split a dollar bill into 4 quarters, a US dollar bill into 4 quarters, you would have quartiles of the distribution. And we're going to look finally at we're going to revisit the tally function and counting, and then we're going to sort that tally function. Because not only is there a spread and central tendency, but we can also think of numerical data as counts. We can think of this in terms of counts in so many applications, and it's a very important measure as well. Not simply the mean and the central tendency, but the number of items or the number of reports, for example. Or say, for instance, the number of points made by a basketball team in a particular game. So we're going to look at these using the data that we had examined in an earlier tutorial to look at row subsets. So let's open RStudio, and we're going to open our data frame, and it asks me here, it's asking me if I want to open this, and I'll say yes, and we load the data frame. But I'm going to close it off, and I'm actually going to go back to the beginning of this syntax here. I'm going to clean this global environment, and you can always use that little brush here just to sweep away your environment. Here, you can actually use a keyboard shortcut, and you can look at a few right here. If you want to clear the console, it doesn't do anything important, but it does clear the space. It's like wiping the table clean. It gives you a nice tabula rasa, as it were, to begin. And we're going to start as we usually do. We're going to load our Mosaic package. We're going to install our Mosaic package, and we're going to install our library, and we're going to install the, we're going to load the data, our data, and we're going to restart. And here you're seeing us download and install the package, and you see it says it cannot remove the prior installation package. That's actually shouldn't be a problem as long as we have Mosaic installed. Let's see if it says it can't remove that. That's fine. This is real life. Let's just make sure that we have this loaded as a library. In fact, there we are. This is really all we need. We shouldn't run into any problems here. The fact that there is an error there really suggests that underscores the point that you don't have to install a package every time, but you should always call the Mosaic library every time, or any other user-written package that you want to use for that particular R session. And we loaded the data set using the script I provided here. Of course, we could always use the drop-down menu too, which we had seen earlier. I'm going to go over past some other syntax, and we're going to go right here into this section number 2 entitled Summarizing Numerical Data. Let's look at this data set of popular kids and look at the distribution of grades. Remember, this is a numerical variable because it's a measure of how important do kids rank grades. So if this is a sample of kids that would really highly rank grades, then we'd expect more 1s. If they don't really on average, it'll be more toward 4, and we'll see what they do. Well, it looks like we have a little bit of an error here. Let's see if we can get that fixed. We'll try to, let's upload this library one more time and see if we can fix this. Okay. Let's look at the names. Make sure we have the actual names of the data. Popular kids. And in fact, that is actually the correct variable. Let's see if we have favorite stats. And in fact, that is there. Fav stats. So what is missing here? You know what's missing here? I will tell you, a tilde. It gets the best of us. Remember the Mosaic package. And this is a common mistake because a lot of functions in R don't require the tilde. This is something unique in the pedagogical style of the people who had written the Mosaic package, which is you have to have a tilde because we're creating a formula. We're saying we're combining a bunch of arguments and we're going to say that this results in what? And this is why it didn't work. Okay, so this is the virtue of patience. You have to be right on when you're writing syntax. If you have one little thing off, there you go. So it gets the best of us. Trust me, I've encountered this many times. So look at this. Here we have 1, 2, 3, 4, 5, 6, 7. 7 statistics here. Usually the favorite 5 I've often counted are the the minimum, the first quartile, the median, the third quartile, and then the maximum. Those are typical. That's often called the right? Yeah, the 5 numbers summary, because it gives you a good idea of where the values lie if you're going to split it into 4 pieces in terms of the relative distribution of counts. You might have a bunch of people in some level, but not in another. Now, it's not as informative here because remember, we only have 4 values here. It's not a categorical variable, as we had discussed when we looked at the row items. It is actually a numerical variable because it's a ranking. Think of it like the Olympics. We are ranking something. The numbers matter. They are relative to one another. So here we get a little bit more information when we look at the mean and the standard deviation. So on average, okay, the grades are not ranked, the highest. It's closer to 3 than it is to 2. It's about not a gold or medal or a silver medal, but it's almost a bronze medal. The standard deviation tells us something else, and this is the spread. So just as an average of something is not determinative, this is the important point when we talk about the spread of a quantitative variable or numerical variable. There is a law of averages. We can predict things on average, but there's also a flaw of averages. Variables, by definition, vary. In fact, that's where the term variable comes from. These last 2 numbers just identify the number of missing cases if we had missing values, which is very common in data collection, and the total sample size. Okay, now we're going to move to elements of these. We're going to look at the central distribution. We're going to look at the median and the mean. Interesting that these are quite different, right? These are, like with statistics, there are many different ways to measure something, and they provide different insights or angles into what the data look like. And this is why it's important to try different things out. It's triangulation. Let's look at this. So we're going to look at the grades. We have the tilde there. I'm double checking. And we see there's the average that we had from the favorite stats function. And then we're going to redo the median rather. And here's that number, that 3. So median is the 3 measures of central tendency. The mode is the most common one. The median is the one that splits the sample more or less. It's a little bit difficult to evaluate this when we think about four values in a numerical variable, but basically it identifies the fact that we have a mean, which is in a sense artificially constructed, and the median is actually an actual value drawn from the sample. And what this suggests is that the average is slightly different than the median. Well, what does that mean? Well, the average the mean rather, can be pulled one way or another way. The classic example we can always talk about is that of a college dropout, a Harvard College dropout. If you look at the average income of a Harvard College dropout, you'll see that you will gain untold billions of dollars. That's because Bill Gates is a famous Harvard College dropout. So you can look at, of course, I'm not dismissing many Harvard College dropouts. Matt Damon is another one. We could probably look at quite a few. But I wouldn't necessarily say that's an argument in favor of dropping out of college, per se, especially Harvard College. I think it's worthy to pursue and complete your education. But the point is, it only takes a few data points to really move that mean, that average, way across on one side or another. It'll take one Bill Gates. If we looked at, say, in a broader example, let's look at college dropouts in the United States. That average is going to be very skewed and misrepresented by the fact that Bill Gates is the richest person on the planet. So that's where we want to also look at the median. And so when the mean is lower than the median, it really says the sample is perhaps pulling in the other direction. It's a little bit higher than we might think because of a few cases that are bunched up on that on toward 1 rather than toward 4. Nevertheless, we see a distribution that pretty much doesn't seem to value vis-a-vis the other attributes, grades, sports, and looks. We all want to be good looking. We all want to be wealthy. Well, who doesn't want to be athletic? Still, grades don't seem to be the highest there for elementary school kids in the United States. I'm sure that's different for different samples. So those are two very simple measures of essential tendency. Another way to express this is some with the width function. It's just another way to do something. It's not necessary. You don't have to think too much about it. But all it says is it's sort of like writing a sentence. You're saying, with this data set, and you have the comma with the arguments, I want to know the average of grades. And notice you have the syntax is a little bit different. I'm going to break this up a little bit like you would parse a sentence. There you go. You see with this data set, you want to know the grades. And you've got to put grades in parentheses. And if I err on this, then I don't, well, look, I didn't. So this is a classic example of why, sometimes the best of us get tripped up with syntax. Because the tilde, someone had asked before, a great question, why do we have that tilde there? That's just the way they want you to express these kind of functions using the Mosaic package. And I think it's great pedagogically. It helps you think things through. But here's another way. You're saying, well, let's put that's the median. Okay, so here we have the mean and median. Expressed the same way, different method. It just goes to show you can find many, many different ways to evaluate. Often the term we often use is evaluate a function or evaluate a line of code, or execute. It's a bit more dark. But here we go back to a Mosaic function. This is the variance. This is a measure of spread. And what we have here is we have the tilde that says we want to know blah, the variance given grades, and this data frame, this data set. And there we are. That's the variance. Okay. What does that tell us? Well, it tells us it's a measure of dispersion. The standard deviation is far more common because it's essentially on average what is the dispersion. What I want to show you here is what we have done earlier is this idea of nesting functions, when we did some rounding. And this is what's also cool about R, is here you have this little variance function, right? We calculated variance. This is identical to this little sucker right here, right? All we're doing is we're putting the square root of this variance. Now what are we going to do? What are we going to see when we do the square root of the variance function? Are we going to see 1.16758? No, we're going to see the standard deviation. That tells us something quite important, that the variance is the square root of the standard deviation is the square root of variance. So that's just a nice little illustration there of nesting. It's not relevant for necessarily analyses. We're going to move quickly through these. Again, the structure is the same. Here we have the range. We know this to be the case. Kids are asked to rank 1 to 4 grades, their importance. Of course, we're going to see that in the sample, but not always. Maybe no one would have reported 4 if we had a smaller sample, or no one would have reported a 1, for example. The interquartile range is something we had discussed earlier. This is, if we split it into quarters, this is a measure of central tendency, and it says that range of central tendency is 2. Well, that kind of makes sense. You got 4 values. The middle 2 are kind of hanging in there as the central tendency. Lastly, we're going to look at something here that could be expressed, I think, in nesting, but I kind of want to illustrate this idea of objects. We're going to revisit our old friend, the tally function. We're going to do this little thing called the assignment operator that we looked at when we subsetted data, and we're going to talk a lot more about this assignment operator. It's a key component of the RStudio language. It's very useful. But think of it as an arrow that says we are defining counts. Okay, so think of that arrow. We got all this stuff on the right-hand side of the equation, the syntax, and then it defines this. This is a definitional statement. We're saying we're going to define counts as blah, everything after this assignment operator. Technically, you can use an equals sign. It's considered bad practice, actually, because an equals sign goes both ways. And what we're doing is we're defining this. This is an object. Look at this. I highlight it because RStudio is trying to help me. It recognizes the fact that when we define an object, we're going to probably use it somewhere else. In fact, it even highlights the fact that I have it in the comment here. But let's look at this. We're going to define counts. And what is this? This is the tally of grades. It's the count of kids by level of grades. And then we're going to sort the counts. So here we represent the counts in terms of the relative distribution. So you see, as expected, from the median and the mean, okay, well, the average is somewhere around here. This is not an order. I'm sorry. This is an order in terms of the number of kids in the category, not in terms of their rankings. So the rankings are 1, 2, 4, and then 3. 3 is the least. So, 3 is the most. The fewest kids are actually prioritizing grades as number 1. A little distressing, perhaps, but at least 4 is not the lowest value. So that's, in a summary, pun intended, what we're doing when we do, I think, what is easily accessible with our favorite statistics. And I want to end with just perhaps something that we all like to do, which is we don't have to have precision to 10 decimal places. Let's round this and recall. I didn't really explain this necessarily, but the rounding function is you take something and then you round it to some integer of decimal places. We can type it 0. There has to be something there. So here we're going to take our little our report of these statistics of these kids, and then we're gonna round it to 2 decimal places. That seems pretty appropriate. Why not? When we talk about mean and we talk about 4, and that's a little bit of a better number here. So, we'll even put 1 here. I don't even know if you really want to see that much detail. Right. So the minimum is 1. Okay. The median is 3. Maximum is 4. You got the mean of 2.6, about 2.5. On average, it's about, varies by 1, and that's 478 kids. In the next session, or the next R tutorial, we're going to look at these visually. And I think this is very important because it's one thing to look at the numbers, but your eyes can sort of glaze over, which is also why I like to round these decimal places. We don't have to have 20 significant digits. I could pretend to cite pi to 20 digits, 3.14, 5, 7, 3, 4, 9, 12. I could impress people because who cares? Not that it isn't impressive to do, by the way, but especially on Pi Day. But the relevant fact here is we're interested in the overall big picture here. We're not interested in exactitude. We're interested in the distribution, the shape. What does it look like? We want to see it. And these numbers will help you see it. The more you look at it, the more you get used to it. The more you play around with the data, the more variables you look at. But we will even see more when we look at the plot function here. And we're going to look at some very cool graphs that look at distributions of the data. Thank you very much, and we will. I'll see you in the next tutorial.